Hello AP Statistics students. In this video we're going to take a look at whether or not a distribution or a data set can be described as normal. We've been learning a lot about normal distributions, how to calculate percentages underneath the normal curve, but we can't use the normal curve unless we can say definitively the data we're looking at is relatively normal. So how do we assess this? That's what we're going to look at right now. So our objective, we will assess whether or not a data set is roughly normal. Again, it doesn't have to be perfect. And we will do this two different ways. First, we're going to use the empirical rule, the 68, 95, 99.7 rule. And the second way is with a normal probability plot. We'll get to what that is in a minute. So here we have a dot plot and summary statistics for some breakfast cereals and the amount of calories in those breakfast cereals. I wonder where this chocolate coated cereal is in those dot plots. Is this distribution roughly normally distributed? Okay, well, it certainly looks bell-shaped, doesn't it? I mean, I can draw a bell curve over it, something like that. But is that bell curve too steep? Is it actually a normally shaped bell curve? So remember, if it is, this bell curve here with the mean in the middle, all right, if we go out one standard deviation, okay, if we add one standard deviation, subtract one standard deviation, remember that should give us 68% of our data. So that's what we're going to do. We're going to go plus one standard deviation and minus one standard deviation from the mean. And if 68% of the dots are in that range, it's looking pretty good. And then we'll go out two standard deviations. And if there we have 95% of our data, it's still looking pretty normal. And then we'll do that one more time and come out three standard deviations. And if within three standard deviations we have 99.7% of all the dots, then we'll say that this is roughly normal. So let's do that here. All right, so our mean and standard deviation, they tell us that already. Our mean is 106, our standard deviation is 19.4. So we're going to take the mean, the middle, add and subtract one standard deviation. So that's 106 plus or minus one standard deviation. That gives us a range. So when we subtract it, we get 87. When we add it, we get 126. And so to give us a quick picture, 87 would be roughly right here maybe. And 126 would be about right there. So if we counted up all of these dots here, I'm wondering if 87 is actually right here. Something like that. And if we count all of those dots, we get 63 out of a total of 77, which gives us 81%. That's not looking very good. That was not 68% like it was supposed to be. Not looking good so far. So now we're going to go out two standard deviations and see if we have 95%. We could probably call it here and say this is not normal because we didn't have 68% within one standard deviation or even anything close to it. But for the sake of practice, let's look at the next one. So we go out two standard deviations this time. So it's the mean plus or minus two standard deviations. So you just multiply 2 times the standard deviation. Add and subtract that number, and you get a bigger range this time. So 67 is probably about right here. And 145 is probably about here. And so you count up all of those dots, and they got 71 out of 77, which is 92%. That's closer, but it's still pretty far away from the 95% that we were expecting. So it's still not looking very good. And if they go out 3 standard deviations, they went all the way down to 48 and up to 165, which does encompass all of them. Which Here, there is not much difference. 100% versus 99.7. That's nothing to scoff at. But really, this sealed the bag. This is not normally distributed, because within one standard deviation, they've got 80% of the data when they should only have 68. That is too big of a difference. Okay, so we could write something that said, all right, these breakfast cereals are not normally distributed because 81.8% of them lie within one standard deviation of the mean. Okay, so that is not, even though it looks slightly bell-shaped, it's not a normally distributed bell curve because too much is in the center. All right, let's do one of those that isn't completely worked out. So IQ scores, are they normally distributed? Many people believe that the distribution of IQ scores follows a normal distribution. Is that really the case? To find out, researchers obtained the IQ scores of 60 randomly selected 5th grade students from one school. Here are the data. All right, thankfully they ordered them from least to greatest as well. We also have a histogram and the summary statistics. Is this normal? Now, if you look at this histogram, you might say, well, no, it doesn't quite look good enough, does it? I mean, it's kind of close, but perhaps that's not good enough. Well, you can't just look at the histogram completely. You should actually test out the 68, 95, 99, 7 rule. So our first standard deviation will be the mean plus or minus one standard deviation. Okay, so our mean is 114.9 plus or minus one standard deviation, which is 14.8. So what range does that give us? So we'll put that into the calculator here, 114.9. I'll do plus first. 1 times 14.8. And we get 129. So that's the larger value, 129.7. Now the lower one, change that to minus, and we get 100.1. So how much of our data is that? 101.1. So I just don't include the 101s because those are a little bit too small. So I'm going to start at the 102s, and I go all the way up to 129. So that will include all of these here, it looks like. So I've got all of that data there. So how much is that? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 times 3 is 33, 34, 35, 36, 37, 38. So that is 38 pieces of data out of a total of 60. So what percent of our data do we have there? 38 divided by 60. We have 63%. All right, that's looking pretty good. I mean, we were expecting 68, and nothing is perfect, right? So that might actually still be plausible. This is looking okay so far. All right, so now we're going to do the mean plus or minus 2 standard deviations. So that'll be 114.9 plus or minus 2 standard deviations. So let's type that 114.9. Let's do minus first this time. 2 standard deviations, 2 times 14.8. I should be good here because the calculator, I think, will do order of operations. It will multiply before adding and subtracting, so I don't think I need parentheses there. 85.3, that looks reasonable, so I think it did it right. Second enter brings that back up and turn the plus or the minus into plus, and we get 144.5. All right, so now we're gonna go down to 85. That means I'm gonna add to here and up to 144 to here. So I had 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57. That gives us 57 out of 60. That's looking pretty good. What percent does that give us? Oh, 95% exactly. I'm guessing the last one will work. Now we're going to do 3 standard deviations. So this is the upper value. Oops. Why didn't that change to a 3? There we go. So now I'm going 3 standard deviations up. That puts me at 159, which definitely goes all the way to the top. So I'm going to have 100% on that side, it looks like. What if I go down and subtract this time? Oops. 70. Does that give me all my data? Yeah, 81 is the lowest my data, so 70 definitely gets all of it. We now have 60 out of 60, so that is 100%, which is really, really close to 99.7. So that is pretty darn close to the empirical rule, all right? 68, 95, 99.7 is all really, really close. So I think we are safe in saying that, what are we talking about again? Context, 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 IQ scores. These IQ scores are roughly normally distributed because they roughly follow the empirical rule. If I could spell the word empirical, that would be nice. There we go. Let's make that a little bit bigger for us. So that's how we can see if some data is roughly normal by just seeing, does it follow the 68, 95, and 99.7 rule, the empirical rule. And so you just count the dots, count the amount of statistical data points in between those intervals by adding standard deviations, and that will show you. All right, but that's not the only way. There is also this thing called a normal probability plot. It's a little complicated to understand what it is, but once you kind of have that understanding, it's really easy to interpret, which is why I want to show it to you. Okay, so a normal probability plot is a graph where the x values are the data values, and the y values, this is the confusing part, are the z-scores those data values should have if the distribution were in fact normal. Okay, so your x value will be a data value, and your y value is what that z-score would be or should be if this is in fact a normal distribution. Okay, so here are the IQ scores, and here's what that normal probability plot should look like if it is in fact normal. So the key characteristic here that I want you to see is that this is a linear line. Okay, and so I'm going to write that down. That is the basic value that I want you to understand, because I might lose you on the next part. So if the distribution is normal, then the normal probability plot, the normal, whoa, that is not a B. Will be roughly linear. That's the main idea here. So if I see a probability plot that is linear, I know that that came from a roughly normally distributed data set. All right, but let's talk about where do these dots come from. You never do this by hand, certainly. It's too tedious, but I at least want to show you how 1 point is calculated. It'll help you sort of understand what the heck a normal probability plot actually is. Okay, so I'm going to pick one data point. Right here, the 130. There is one data point right here at exactly 130. So where does that point go on a normal probability plot? Well, the x value is the data value, 130. The y value is the expected z-score. All right, over here, the expected z-score that value should have if this is normal. So how do I figure out that? Well, I find the percentile. All right, what percentile is 130? So I counted these dots for you. All right, on the left, including the point, there are 50 dots. And on the right, there are 10. So our percentile is equal to 50 out of 60. All right, it is greater than or equal to 50 of the values out of the 60. So that gives me a percentile of 50 divided by 60. That is the 83rd percentile. All right, now if this were normal, what z-score would the 83rd percentile have? Well, that's what I'm going to calculate. Now remember, the 83rd percentile, if this is normal, here's my quick normal curve. Here's the mean. The 83rd percentile will be somewhere over here. And that means that 83% is the area to the left. Well, that's an inverse norm. I want to know what is this value where 83% is on the left. So I'm going to go to my calculator and inverse norm that. Inverse norm. The area, I want it to be 0.83. I think I can even add a few more threes in there, right? Didn't it have 3 repeating? The mean is, where are my 114.983. And the standard deviation was 14.8, roughly, 14.8. Paste that in. So this should have a, oh, I didn't want to actually put the numbers in. I'm sorry, I'm gonna go back to their inverse norm. I almost had it all right. This is a z-score, so I want that mean to be 0 and the standard deviation to be 1, a standardized normal curve. That will give me the z-score. I don't want the data value. There we go. This should have a z-score of 0.967. So this value right here should be 0.967, just below 1 standard deviation from the mean. So that is my y value, 0.967. That is the z-score it should have if in fact this distribution is normal. So we would come over to our graph, 130, and it would come up right here to this point, which is somewhere around 1. 0.96 is basically 1. So that is how you plot this. Now you, again, never do this by hand, but if you do that for all the data and it comes out to be a linear line, that means your data set was roughly normal, okay? So I could say for this one, these IQ scores are roughly normal. Where was my sentence? These IQ scores are roughly normally distributed because the normal probability plot is linear. Same type of sentence, but my because statement is slightly different. All right, and one more. Take a look at here. So here we have the number of siblings in a sample of people. All right, is this normal? Hopefully just by looking at it, you can say, well, no, this is definitely skewed to the right. What does that look like in a normal probability plot? Right over here. So I'm hoping you can see that there is a definite curve in this normal probability plot. It is not linear. So we would say that the number of siblings, all right, so the distribution of the number of siblings in this sample of people is not normally distributed because the normal probability plot is not linear. It has a definite curve. All right, and that's enough to say now definitively that that distribution is not roughly normal. All right, those are the two ways that we can take a look at a data set and assess whether or not it's roughly normally distributed. You can do the 68, 95, 997 rule, or take a look at a normal probability plot.